Hi, my name is Roy Bolaños. Welcome to the analysis design of a flyback converter. This is video 28. Uh, Now this is a good video to watch. I want to discuss some of the features of the simulator that I'm using. I am using Top Spice. That's my preferred simulator. There's other simulators like LT Spice, which is free, but I still like Top Spice because of the models that are included with the package, and it offers some pretty good features. Okay, so anyway, so this is the topic they're going to be talking and showing, and it's a topic of AC simulation using a switching model. Okay, so typically there's two models. You're either going to use a average model, and if you use an average model, those are used to do loop analysis. In other words, if you want to do your loop analysis, see what your phase and gain are going to be, then you would do a loop analysis using an average model. So you have to derive a model. Okay. So there are several models that are out there. You can use the Vacha model, you can use the Ridley model. I use a very simple model made by my mentor Jack Alexander. Okay, so then the second types are used for transient analysis, okay, which is number 2, and these are models where you can see the voltages, the currents, and with that you can see the timing. Okay, and typically these take longer to run. Okay, and they're slower too. And these, when you do a loop analysis, are typically fast because you're not calculating any voltages or currents. Okay. However, there are a few simulators that you can extract the AC analysis or the AC information using a switcher model. Now this is very powerful. In that if you only use a switching model, and you can extract both your switching and your AC analysis using only one model, I mean, that is great. So this is what you really want if you can have a simulator. And as far as I know, there's 2 simulators that do it very well. It's the Simplest and PSim. Now these are very fast, okay, and you can extract the switching, meaning like the voltages, the currents, and the timing, but you can also extract the AC models. But one of the drawbacks is they're not Spice compatible. In other words, they use their own model, and usually they're simplified. Okay, so you lose a little bit of accuracy. And that may be okay. Okay, so now some of the simulators like LT Spice have become faster and faster, and they're fast enough now that you can perform simple AC analysis. Okay, so I just want to show one of the models. This is one of the models, and this is from the Ridley's Works and it's a LT Spice Schematic. Basically, it's the model. He's using this model here, and here's your power plant. Okay, and these are the parameters. It's working at 36 volts input. The output is 5 volts, 1 amp, and so forth. Now, really has implemented this, and I believe this may be integrated into his software, which is a very good software. And by using this software, I believe there's a little button where you can extract your design that you have in Really Works and exports it to this. And once you have this, this is your FRA, frequency response analyzer. It's the AP300, and it emulates a frequency response analyzer. And then of course you have some parameters that help control the timing and so forth, or the analysis. Okay, so once you have this, all you have to do is press run. Okay, let's see, there it's running. And if I go here, you can actually see what it's doing. And if you notice, what it's doing is it's injecting a signal into the feedback. And if you notice, this is connected to this side. So this is the feedback, and it's checking the phase difference between this connection and this connection. So let me see if I can plot. This is, I'm plotting B. Let's see if I can add a second plane and see if I can plot this. Okay, so this is B side and this is A side. So he's generating a signal, and that signal is compared with this signal, and he does a series of where he compares the amplitude and the phase difference. Okay, and from that you can extract a Bodhi plot, and he does it over a certain frequency. In this case, if you look at his text, he's plotting from 300 to 1 meg at 5 points per decade. Okay, so I'm going to go ahead and halt that. Okay, so basically you can extract that, and at the end you end up with a Bodhi plot that looks like this. Okay, so that is what you want. This is your AC information. Okay, so now I want to show that this is basically the same schematic. I duplicated the same schematic that Really Works does. I have the same values. The only difference is my PWM is a little bit different. I'm using an 1843, and the value of this current resistor is a little different. His value is double. I had to cut it in half because the current sense limit on this one is 1 volt. The PWM that Really uses is 2 volts, so I had to scale it down. But anyway, this is the schematic. Okay, and to do a Bodhi plot or a FRA, you're going to need a signal source. Here's my signal source, and in this case I went ahead and labeled it as VFRA. Okay, and then you have to make sure that you define a amplitude. In this case, it can be any voltage. This really doesn't matter right now, but in this case I'm going to put 1 volt and a frequency of 1K. Okay, and I already labeled this as out, and this is in. Okay, and then one thing that I do to speed up the simulation, because the simulation does take a long time if you let it start from steady state. Okay, what do I mean by steady state? Or to reach steady state. Okay, so since you have a power supply and you have the capacitors, okay, so you're charging this cap. So this cap takes time to charge up, and you're charging from 0. In this case, it's going to charge from 0 to a steady state of 5 volts. Okay, so there's a time where it reaches steady state. Okay, so this time can be long. It may take 1 millisecond, or it may take 10 milliseconds. Okay, so if you have to do a simulation, you have to do a simulation for each frequency. In this case, I'm going to start with 300 hertz, and you would have to, let's say if it's 2 milliseconds, you have to run a simulation for 2 milliseconds and then do the excitation. In other words, you want to inject the 300 signal into the system, and then all of that takes time. Okay, so to simplify this, what you can do is you can do a pre-run, and basically you let it run and you see what is the voltage that this capacitor will eventually reach. It will be, obviously it's going to reach, in this case it's 5 volts, so you set this to 5 volts. Okay, and then you also set the voltage that this capacitor will reach. Okay, so you initialize them. Okay, so that will speed up your simulation. Okay, so now let's go ahead and go up to setup, and to use the FRA, you go to the transient analysis, and you have this icon that says setup. Okay, so I'm going to go ahead and explain what this is. Here, the first thing you want to do is, wherever your signal stimulus is, in this case it's VFRA, that's the name of the stimulus, you define it here, and then you can put in the frequency that I'm starting. In this case it's 300, and I'm going to go ahead and stop at 247. Okay, and then if you put a decade, then you put how many points per decade. Okay, so now this is some more settings. This is the steady time. That's the time that it takes for it to reach steady state. This time. Okay, the time step is the steps that you will use in the simulation, and then this time run maximum, you want, this is the limit. Okay, and the way you set that is, I usually set it for where I can get two cycles of 300, or your lowest frequency. So in other words, if I get 1 divided by 300 hertz, that is 3.33 milliseconds. Multiply that times 2, so it should be 6.6 milliseconds. So that's the longest time that I want it to run. So what it does, this speeds up your simulation. Okay, and then you have the number of periods. This is the number of cycles that you want to for it to simulate, and then these are the measurement where you will be taking your gain in phase. Okay. Now, one of the things is, or for those that have used FRAs, that if you use the Ridley FRA or the Bodie plot or the Venable, if you use a constant voltage, in this case, if your signal is constant, then at certain frequencies you will get distortion. In other words, as you plot from, let's say, 300 to, let's say, 100K, and your gain should look something like this. Okay, so as you're stepping through the frequencies, if you use a constant voltage, on your stimulus, you will get some distortion across your points. So remember, you're injecting a sinusoidal signal across your injection transformer or points, and you're supposed to get a nice sine wave on both sides. Okay, but if you inject too much signal, you might get a sawtooth looking signal. Okay, so in that case, you might have too much signal. Okay, so one of the things that you do is you vary the signal. Now, if you look at the script that really uses, he starts the amplitude at 250 millivolts, and then he attenuates the signal all the way to 5 millivolts. So in this case, I believe he's using a linear interpolation, and he's varying the signal as the frequency is stepped up. Okay, well, you have the same capability here, except that you can do it at a much finer resolution. In this case, you can set up a table, and here's a table that I've set up. So I put the frequencies that I want it to output. In this case, it's 300, and I want 200 millivolts, and then I want 400 hertz at 100 millivolts, and so forth. So I define that way. As the frequency is stepped up, the frequency goes down, and then in this, there seems to be a resonant frequency at 10K. I want to decrease the amplitude and then increase it back up. And if you notice, like on the last 60K and 100K, I need much more signal because the attenuation at those frequencies are very low. So in this case, I have a very powerful FRA, because now I can specifically set my signal amplitude. Okay, so once I have that, I can go ahead and let it run. It'll probably take about 2 to 3 minutes. So now it cycles to 400, and if you'll notice, as it goes up in value, you will start to see that the simulation will start to speed up because the frequency is much lower. Okay, and if you notice, the simulation time here is 6 milliseconds. So the next one, this should be shorter. Should go to 600. Okay, 600 still, and then eventually this is gonna go slower or get smaller. Let's see if it then it should go to either 2K or 3K. Let's see, what did I set it? Okay, 2K. So now if you notice this decrease, so now it's running a little faster, and then on the next step it should decrease also. Okay, so now it's gaining speed. You're at 253 into the simulation. Okay, now I reduced to 2.2. It's going faster. It's almost there. It's up to 20K. And this should be the last one. Okay, so here's the plot. Here's your gain. This is your face. Okay, so let's go ahead and we're going to go ahead and move this. We'll cut that and we're going to paste it here on one. And let's go to options, and I want the face in light red. That looks prettier. Okay, so I go to axis options and I want to put this in log mode. Okay, so I'm up to here. So let's go to limits, and I believe I started at 300, so I'll set this at 300, and then let's see at what frequency. Oh, no, 100 dBs. In other words, the axis. I want to see where the axis I'm going to set it to. There you go. It's actually this one. Okay. 100. 100. Okay. So now you have the body plot. So now you can copy and paste it, which I've already done. Or actually, let's go ahead and actually like this one better because it's got color. So I'll go here. Okay. Let's see. Can I paste this? Yeah, I can. Okay, so now if you look at this, okay, that looks pretty good. This is crossing approximately at about 20 with the phase margin at about 60, and here this is crossing at 10K with a margin of about 40. Okay, so keep in mind that the PWM that I'm using is different from the one that he's using, so there's going to be some differences, but if you look, they're pretty close considering that I'm using a different PWM. Okay, so this is pretty powerful indeed, that you can go ahead and use a switching model. Okay, and you can extract. Now let's say if you wanted to extract the power plant, well then you would plot a V out versus EA, and to do that all you have to do is go to the transient, and then here you would put out and then change this to EA. Okay, or let's say you want to plot your signal or your error amp transfer function, then you would do a transfer function, or you would do a EA to in. So you would go here, basically EA to in. Okay, so let's go ahead. I'm going to go ahead and do that. See how's it look. and then approximately 4 minutes. Let's see, will it beat it? Yeah, approximately 4 minutes. 354. Then you have this Bodhi. Go ahead and cut, paste. Okay. And then we're going to go to options. Okay. And if you'll notice, this is the gain. So here's the gain, and this is the phase. Yeah, I think there's a, okay, that looks a little different. I think I had plotted that before. Oh, okay. It's showing this here, this portion, because I'm plotting from 300. 300 would be here. So I should get basically this part. Okay. So I really need to extend that. Okay. So I'm going to do another simulation of that. Okay. But anyway, it looks okay. So just being able to do this type of a plot and extracting it using a switching model and having at least a little bit of confidence, or at least having the idea of where you're switching or your crossover and your gain would be, gives you a better feel of how your power supply is operating. Okay, well that's that. If you have any questions or comments, you can drop me email at rbola35618 at aol.com, and if you like, please share, give me a thumbs up, and subscribe. Thank you for watching.